I'm going to show you 5 techniques that encode protocols directly into your type system. Each one targets different scenarios, and I'll show you exactly when to use each. Fluent interfaces with state-specific types works perfectly for simple linear protocols with clear state transitions. The fundamental insight is that we can use the type system's interface mechanism to represent states and method return types to represent valid transitions between those states. Let's understand what's happening in our database example. We start by recognizing that our database connection exists in exactly two conceptual states. It's either idle and ready to begin a transaction, or it's actively inside a transaction. These aren't just implementation details, they are fundamental to the correctness of our program. The connected interface represents the state when no transaction is active. In this state, the only valid operation is to begin a new transaction. Notice that the begin transaction method doesn't return void or the same connected interface. It returns a transaction interface. This return type is the key insight. The method call doesn't just perform an action, it transitions the object to a new state with a different set of valid operations. The transaction interface represents the active transaction state. Here, you can perform read and write operations, and these operations return transaction again, meaning you stay in the same state and can continue performing more operations. But the commit and rollback methods return connected, representing the transition back to the ideal state. What makes this powerful is that the implementation class, or DB class, implements both interfaces simultaneously. At runtime, it's always the same object, but the compiler sees different views of that object depending on which interface reference you're holding. When you call begin transaction and get back a transaction reference, you're not getting a different object. You're getting a different view of the same object that exposes only the methods valid in the transaction state. The type system enforces the protocol because once you have a connected reference, the compiler literally cannot see the commit method. It's not part of the connected interface. Similarly, when you have a transaction reference, you cannot call begin transaction again because it's not part of the transaction interface. The protocol violations become compile type errors here. This approach leverages the existing type system without requiring any special language features. The interface mechanisms that already exist for abstraction and polymorphism get repurposed to encode state machine transitions. The fluent method chaining makes the state transitions explicit and readable. You can follow the chain of method calls and see exactly which state you're moving through. Now, the limitation here is scalability. Each state requires its own interface. And if states can transition to multiple other states, you need to carefully design the return types. For a protocol with many states or complex transition graphs, the number of interfaces can become unwieldy. But for simple linear protocols, especially those that follow a clear setup, work, teardown pattern, this technique provides maximum clarity with minimal complexity. The second technique is phantom type parameters. Now, when the interface per state approach becomes too verbose, phantom type parameters offer a more scalable alternative. The key insight here is that we can decode state information in the type system without that information existing at runtime. Let's break down what's happening in our phantom type example. We start by defining our states as actual types, idle and in transaction. But these types carry no data. They exist purely to be used as type parameters. The sealed interface pattern ensures that these are the only two possible states, giving us exhaustive checking. The DB class is now parameterized by state. This means that every instance of DB has a type parameter that tracks which state it's currently in. But here's the crucial part. This state tracking happens entirely at compile time. At runtime, all DB instances are identical objects. The state parameter is phantom because it influences type checking but has zero runtime representation. The magic happens in the method signatures in the cast helper method. When you call begin transaction on a DB idle, the method signature tells the compiler that it returns a DB in transaction. But what does the implementation actually do? It just casts itself to the new type. The object doesn't change at all, only the compiler's understanding of what type it is. This casting might seem dangerous, but it's actually safe by construction. We've designed the API so that the only way to get a DB in transaction is by calling begin transaction on a DB idle. And the only way to get back to DB idle is by calling commit or rollback. The casts simply reflect state transitions that we've already guaranteed are valid. The method availability is controlled through method overloading and type bounds. You can't call commit on a DB idle, not because the object lacks the capability, but because there's no method signature that matches DB idle as the receiver type. The compiler sees that commit is only defined on DB in transaction and rejects the call. This approach scales much better than multiple interfaces. You can have dozens of states represented as simple marker types, but you still have only one class to maintain. The state transitions are encoded in method signatures rather than interface hierarchies. Type parameters can be composed. You might have a DB state access level to track both protocol state and security context simultaneously. The downside is complexity in the type signature. Every method that works with DB objects needs to specify the correct type parameters. Generate type inference helps, but error messages can become confusing when type parameter constraints aren't satisfied. The casting, while safe, requires careful design to ensure that runtime behavior matches the compile time type transitions.